All right, so let's focus on each of these angular quantities in a little bit more detail. All right, so what's nice about theta is, strictly speaking, it's angular position. So it's a way for us to precisely state the location of a point for an object that's moving in a circular path, right? Whether this is a whole object or a point on an object that's moving entirely. Right, so for example, typically it's convenient to call, well, it's going to be most convenient to call the initial location and angle location of 0. Um, so if that angle changes, or so I should say, if the object moves from one location to another, one angular position to another angular position, it displaces, and this is called angular displacement. Right, so there is our visual of our object starting at one angular position and it rotates to another angular position. So it has an angular displacement that's equal to the final angular position minus the initial angular position. Just like how displacement delta x was your final position minus your initial position. Same thing. We're just saying that our position is in terms of angle. The unit we're going to use here is the radian, which is a misnomer because it's not actually a unit. As you can imagine now, well, if we have an angular displacement over a certain amount of time, we will then have an angular velocity, right? So this tells us how quickly the object changes angle, right? Or I should really be more precise here, how a point on an object, how fast that angle changes. So this tells you how quick the rotation is. So, right, so here we have that point moving and a difference in time. So that change in angle divided by that change in time will give you average value for angular position. Right, I use the word average here because this is really, we're going to get into some angular kinematics later. So in terms of units, in our numerator, we have angular displacement, which is in radians, and in the denominator, we have time, where the SI unit is seconds. So we have radians per second. Now what's interesting about angular velocity is that it's the same everywhere on an object that's rotating, right? So really, when we're looking at these images, what you should be visualizing is maybe some sort of disk that's rotating, so a solid disk, where we're looking at the motion of one specific point on the disk. So if we had a disk, maybe we drew a dot on it, and we're looking at the motion of that dot, right? So that's what these pictures here are showing. So on the left here, we see that that dot moves from one angle to the next. All right, so if we were to look at the angular velocity, we could compute that with the angular displacement over time. But if we wanted to know the speed of that location, really what we're dealing with is the tangential velocity here. That's going to be the arc length, that distance over time. So if we were to throw some numbers here, let's say that the angular displacement is a quarter pi. So if we were to use degrees, 90 degrees, but we're not. And let's say that the radius is 255 meters. Therefore, the arc length is 0.4 meters. Right? So in computing that, we find that the angular velocity is 0.25 radians per second, where the speed of this object, the tangential velocity, is 0.2 meters per second. So that's kind of a point that's in the middle of this rotating disk. If we're looking at a point, let's say at the edge of the disk, let's have it do that same quarter turn. Right? And in that quarter turn, This time, the radius we're dealing with is 0.509, meaning that our arc length here is going to be 0.8 meters. So even though we have the same quarter rotation, so therefore our value for angular velocity is the same, 0.25 radians per second, we see here that this point on the disk moves a further distance because it's further away from the center of the circular motion. So it's moving at a faster speed. So where the angular velocity is same everywhere in the disk, the speed of a point increases with the radius. Right? All right, these slides here are fun. So we can actually convert from here I say from velocity to angular velocity at a certain radius r. So really what these conversions are basically two different points of view of motion. We're looking at the translational motion, the tangential motion, and comparing that to the rotational motion. So here are just the formulas for the angular velocity and the velocity. And I just rearranged these for time, right? Because the time that this occurs, the time that a certain location on a rotating object changes angle is the same amount of time it traces out some path d. So then these times are the same. So we could set them equal to each other. Right? So this relationship could be useful to us, but it might be more useful if we were to reword things, for lack of a better word. Right? So for example here, rearranging, cross-multiplying, we get that the average velocity is the average angular displacement times the distance, that arc length, over the angular displacement. But we know we can define angular displacements as being the arc length divided by the radius, right? Which our arc length here is a distance d. So then we can revert this in terms of radius, because radius here is going to be the arc length divided by the angular displacement. That allows me to do a substitution here so that I can get this in terms of, rather than the distance that the path traces, so that angular quantity, that arc, I want to say arc path, right? We can get it in terms of radius instead, which is going to be more convenient in terms of mathematics. So doing the substitution, we find actually a very simple relationship, that the translational speed for that point is going to equal the radius times the angular speed at the point. Now, let me be clear here. When I'm using this word radius, I don't mean the radius of the entire object. I mean the distance from the distracted by my husband making coffee. And so this is from the kind of the center of the rotation, so the rotational axis, to whatever point you're looking at, right? So it doesn't have to be the entire object, it's whatever location we're looking at. We can use this formula. This formula is not on your formula sheet, but I recommend you memorize it rather than do this whole derivation. All right, so V is equal to omega times R. All right, so if we wanted to convert the linear speed to a point that's moving on a circular radius r to angular velocity, we can use this relationship, and vice versa. Now another quantity, as you can imagine, is going to be angular acceleration. So if a point on a rotating object is not moving with a constant angular velocity, then if it's, so basically if it's rotating faster and faster, or if it's rotating slower and slower, right, so speeding up or slowing down, it has an angular acceleration. Right. So as you can imagine, we're going to define our angular acceleration to be your change in angular velocity over time. As simple as that. In terms of units, we're dealing with radians per second dividing by seconds, so that's radians per second squared. right? We can have a similar derivation here. I'm just going to pan through it. It's basically the same exact thing as last time, but with acceleration instead. And we have a relationship that we can find the tangential acceleration for this object, or translational really would be more of an appropriate word here, is equal to radius times alpha. So A is equal to alpha times r. So if we want to convert the linear acceleration of a point that's moving in a circle at location r away from the center of that motion, we can use this relationship. All right. So what's really nice is that we can basically rewrite our kinematic equations in terms of angular quantities using these relationships. The fact that position is going to be r times theta, so this is just using that arc length formula, with now using a different variable for location. V equals omega r and A equals alpha r. All right, so we can use these analogies basically. So for a position x, we have an angular position theta. For our speed, change in position over time, we have angular speed is change in angular position over time, and so on and so forth. So we can use any of the kinematic equations, and basically anywhere that there is an A, you replace with alpha. Anywhere there's V, you replace with omega. And anywhere there's an X, you replace with the theta. When you do all these substitutions, each of these variables has r in it, so the r's cancel out. So that's pretty cool. So what's interesting is if you look at your AP Physics formula sheet, what you would notice is first they give 3 translational kinematic equations, but they also give 2 of the angular kinematic equations, but not the third, which is very mind-boggling to me. But you can just use that third kinematic equation by just doing these substitutions. So just very quickly here, as an example, so we can compare a kinematic question to a rotational kinematic question. So for example, here we have a car starting from rest. It has an acceleration of 4 meters per second squared for 3 seconds to determine its final velocity. So we write down what we know, and we use the kinematic equations to solve. We can do a similar thing here, but word problem is going to be talking about its rotation instead. So here we have a wheel, and it starts from rest and has an angular acceleration of 4 radians per second squared for a time of 3 seconds. Determine its final angular velocity. So for this example, the wheel starts from rest, so its initial angular velocity is 0, and we want to know its final angular velocity. All right. Our change in angle we don't know. Our angular acceleration is given, and we know the time. So then we can use our angular kinematic equation, the one that does involve angular displacement, to solve, and we end up with 12 radians per second. All right. So in terms of problem-solving strategies, you just follow the same approach as kinematics. Right? So write down what you know, drawing a diagram is helpful, and just be careful with speeding up, slowing down, either being a positive or negative angular acceleration.